Hello everyone, welcome back to Labtube. In this video I'm going to do question 25 from section 16.7. The question asks to evaluate the surface integral of this vector field xi, yj and z squared k. And the surface is the sphere of radius 1 centered at origin, and the orientation is the outward orientation. Okay, so what we need here to know is that if you have a surface integral of a vector field f dot ds, you have to fix an orientation. What's the orientation? Orientation is a vector which is perpendicular at each point to the surface, and it changes continuously and it is unit. If you have that, then your integral is going to be integral of f dot n. You find f dot n, it is going to be a function over your surface, and then integrate over the surface, the whole surface. But it's not practical equality for us. What we're going to use is when your surface is parameterized and the orientation which your parameterization gives is equal to orientation that you're looking for. Okay? So in that case, if S is parameterized by our UV and our U cross RV, which is the vector at this point, is multiple So sometimes I will call that kind of parameterization positively oriented parameterization. So if I have a positively oriented parameterization, then I can go ahead and change my surface integral of vector field to a double integral by doing these three steps. Put boundaries of UV for your double integral. Then plug in your parameters into your vector field. So your vector field will be in terms of parameter U and V. Then find our U cross RV, that's a vector, and then dot product it to your vector field. Your vector field, which is written in terms of your parameters. Then you will get a function in U and V. Then find the integral du dv. Okay, so this is general thing. But now let's do what is parameterization. A parameterization for a sphere, for that specific sphere. Okay, we have done a lot of examples for this questions like this. For a sphere, the best thing would be, for a sphere centered at origin, the best parameter would be parameterization given by spherical coordinate or spherical angles. So here, let me write phi and theta. Okay? For phi and theta, I know that in the spherical coordinate x is equal rho sine phi cosine theta, but rho for us is equal to radius, so it is 1 sine phi cosine theta. Y is rho 1 cosine sine phi sine theta, and z is equal to cosine phi. And to cover the whole sphere, I have to let phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, so this is the parameterization. First thing you have to ask yourself is this the orientation? Is this parameterization positively oriented? Or, in other words, are U cross RV? Is it the outward orientation or not? Okay, let's check that. So I have to find RU. Okay, RU, I mean the first component, then R theta here. R phi is cosine phi cosine theta, cosine phi sine theta, and negative sine phi. R theta is minus sine phi sine theta, sine phi cosine theta, and last component is independent of theta, so it gives us 0. Then let's find R phi, R theta. So cross product this minus this, so it is going to be sine square phi cosine theta. This minus that, it is minus, so it is sine square phi sine theta minus 0. And the last part is this times that, cosine phi sine phi times cosine square sine phi cosine phi times cosine square theta, minus, and I have another minus here, it's plus cosine phi sine phi times sine squared. I can factor out sine phi cosine phi and then write yes. And okay, so I don't need to write that down because cosine theta plus sine theta is equal to 1, and I can go from there. Okay. So the first question you have to ask yourself here is that, is this outward orientation or not? Is it something which is oriented outward or not? In this specific case, how can I see that? The way you can see is that if you factor out sine here, sine of phi, this is going to be sine phi cosine theta, sine phi cosine theta, sine phi sine theta, sine phi sine theta, and cosine phi. So it is going to be equal to it is going to be a multiple of the vector which defines the surface, the sphere. Okay, what does it mean? It means that if this vector defines the surface, I multiply it by something like that. Sine of phi, if phi is between 0 and pi, it is going to be always positive. So I multiply it by a positive thing. So it is going to be in the same direction. So look at here. If you have a sphere, and that point is given by this vector, then the orientation that this parameterization gives us is in the same direction. That means this is outward orientation, or this parameterization. So this parameterization is positively oriented. Since it is positively oriented, then I can use this and change my surface integral to a double integral. So let's do that. Integral of s f dot ds is equal. I'm going to change my parameters, phi and theta here. Then plug in r theta in your vector field. So for x, you plug in sine phi cosine theta, sine phi sine theta for y, and cosine phi for z. Then dot product this guy to the cross product that we found here. So it is sine square phi. Okay, let me write just r phi. R u cross rv. These are in terms, and then d. Okay, there's no uv, so I have to phi theta d phi d theta. Okay. I know that the parameters goes from 0 to pi, 0 to 2 pi. And then from vector field, when you plug in these things, so it is going, first component is equal to x. First component then is going to be sine phi cosine theta. But dot producted to this component, so dot product to sine square cosine theta. So I already have that, so the dot product, first component to first component. So this dot x. Okay, plus. Second component is y, and y is given by sine phi sine theta. Dot producted to this, you're going to get sine to the power 3 sine theta to the power 2. That's good. Plus, last component is cosine phi z. Z is cosine phi, but the vector field, the third component of vector field is z squared. So I'll get cosine squared phi times the third component of this, which is sine phi cosine phi, another, so squared cube. Then d phi d theta. Okay, this is good now because I can try to simplify this. This guy, I can factor out sine cubed of phi here, and the remaining would be cosine theta plus sine squared theta, and that is equal to 1. So these two first terms are going to be equal to sine cubed phi. Now I can factor out sine phi, so let me write it here. Sine phi, then from two first term I get sine square phi plus cosine cubed phi. Okay. It seems that I am in a good shape because, okay, this is cosine. Its derivative is sine phi, negative sine phi. Okay, I have it there. But this is also sine phi. What I can do, instead of sine phi, I can write 1 minus cosine squared phi. 0 to pi, 0 to 2 pi, and this is d phi d theta. Now I can use substitution, set u to be cosine phi. Then we are going to have 0 to 2 pi. Derivative of cosine is negative sign, so I have to put a negative sign here, negative. And the rest is 1 minus u squared plus u cubed du d theta. But if I plug in phi 0, I get 1. If I plug in pi, cosine of pi is negative 1. So everything is there now. Now I can find antiderivative of that. Antiderivative of this gives me u minus u cubed over 3 plus u 4 over 4. Go from 1 to negative 1. I have a negative sign. I kept it outside somewhere. 0 to 2 pi and this is d theta. Okay, plug in everything. It is -1 plus 1/3 plus 1/4 minus there's a minus sign up there, and now I'm plugging in 1, so it is 1 minus 1/3 and plus 1/4. 0 to 2 pi. Okay, so if we do add these things, so I have -2 plus 1, 2 over 3, -2 plus 2 over 3 is going to give us -4 over 3, but I have a negative sign, so it is plus 4 over 3 integral of 0 to 2 pi of d theta. Okay, 4 over 3 d theta, then d theta, antiderivative is theta, go from 0 to 2 pi, it is going to be 2 pi minus 0, and this is equal to 8 over 3 times pi. Okay, very quick wrap up is that if you have a surface integral of a vector field, try to find a parameterization which is positively oriented, meaning that the orientation that your parameterization is giving is equal to the orientation that you're looking for in this question. It was outward, and we were lucky. The orientation that we find was positively oriented. That means that I can use this parameterization, and then I have that parameterization. I change my surface integral to a double integral just by plugging in vector function into your vector field. Write your vector field in terms of your parameters. Dot product it to Ru cross Rv. You get a function, and then integrate that function over the region of your parameters. In our case, we did that. We get a function. We have double integral, change it an iterated integral, do inner one, do outer one, and we computed the value of the surface integral for that vector field. And thank you for watching this video.